Hello and good morning to all of you. I welcome you to this video on big data analytics. In today's video, I'm going to discuss about HDFS architecture. Now this Hadoop distributed file system, it appears as a single disk to the user. As we have seen in the installation of Hadoop, that it runs on top of a native file system. That is, when you install Hadoop, you install Hadoop distributed file system therein. This file system is running on top of an already existing native file system. Like we installed Hadoop on Ubuntu, and Ubuntu is based on the ext3, ext4, XFS file systems. Now your HDFS is running on top of it. And this HDFS, as we saw in our previous videos, is based on the Google's file system, the GFS, right? And it is fault tolerant. It can handle disk crashes, machine crashes, etc. And it is based on the Google file system, the white paper published by Google in the year 2003. Now, if we talk of its architecture, it consists of commodity hardware. By commodity hardware, we mean cheap hardware, okay, not very expensive like in case of supercomputers. But this commodity hardware is unreliable. It is prone to frequent failures. And it is not a desktop. Kindly have a very clear look about it. It is not a desktop. It is arranged in racks, and racks are connected to switches, right? So you can see that your commodity hardware is placed like in racks, right? And if we talk of HDFS as a file system, it is good for storing large files of the size terabytes, petabytes, and we would like to store millions rather than billions of files. And we are assuming minimum 100 MB or more per file. That is what HDFS is designed for. And it is also designed for reading streaming data. Okay. So you just store your file once in the cluster, and then you can read it many times to bring out patterns from the data and analyze the data. And it is optimized for streaming reads rather than random reads. Okay. And append operation has been added to Hadoop, but it's not required. Like mostly we are interested in storing huge files in the cluster and then reading them at a very fast pace to pick up the patterns in the data. And we don't require supercomputers. We just use this commodity hardware, which is less reliable, but it's like it serves our purpose, right? And if we talk of HDFS as a file system, it is not so good for low latency reads, right? And for large amount of small files. Okay, so it's better that you store millions of large files instead of billions of small files. Okay, and like you won't be able to append data to a file. You can just copy a file into the cluster. Now, how does HDFS actually work to store the files and give access to the files? It is like HDFS is managed by three types of daemons or three types of processes. These are namely number one, name node, number two, data node, and number three, secondary name node. So if we discuss name node, it is used to manage the file system's namespace, metadata file block. So it keeps information about the metadata. Like it tells you like which part, which block of which file is located on which machine, right? And it runs on one machine to several machines depending upon the size of the cluster. And data node is like the commodity machine that we talked of, and it actually stores and retrieves data blocks. And it is always reporting to name node. It is always in touch with name node because name node contains the file block locations where the data can be stored. And this data node obviously runs on every commodity machine in the cluster. Then there is an additional process known as secondary name node, which is just a helper to name node. Okay, and it requires similar hardware as name node machine. But it is not a backup for name node, as the name secondary might suggest. The secondary name node is not a backup for name node. Okay, it is simply assisting name node in certain housekeeping operations, which I will discuss with you in due course of time. And so you can see that your HDFS daemons, the name node and the secondary name node, these are the management nodes. Okay, they are managing the cluster, whereas this data node is actually storing the data in the cluster. Now, when we talk of files, see files, when we want to store a file into the cluster, first of all, the file is split into blocks. The block is the single unit of storage. And these blocks are managed by name node and stored by data node. And these are transparent to user. We can actually see these blocks. So in this video, when I go further, I'll be actually showing you all the blocks that a file is split up into. And each block is replicated across machines at load time. So whenever you are loading a file into the cluster, it is first of all split up into blocks and then it is replicated across machines. Okay. So why we replicate these blocks? Because if some of the machines they go out of order, then we can get that file block information from some other machine, right? And by default, the replication is 3. That is, each block is replicated across 3 machines in the cluster. And you can set this to a lower number or to a higher number also. You can set a replication of 6 also, 8 also, 10 also for machine for files which are very critical, right? Which are required by most of the users. So you can increase this replication, but by default the replication is 3. Okay. Now let's see this file. There is a file hamlet.txt and it is split up into 2 blocks. Okay. How the file gets split up into blocks depends upon the block size. Okay, which I'll discuss with you. Okay. And you can see that this block V1 is placed on 3 different data nodes. And kindly see that how it is arranged, that this is rack 1, okay, this is first rack and this is some other rack in the cluster. So usually the idea is to store 2 blocks on 2 machines in the same rack and 1 block in the different machine in different rack. Okay, this is because like if at times there is some problem that an entire rack goes out of order, right? Then you can always fetch this block from some other rack, right? Okay. Now these blocks are traditionally 64 MB or 128 MB. Okay, by default the block size is 64 MB. Okay. So what do you mean by this? That if you have got a 100 MB file and the block size is 64 MB, then a 100 MB file would be split up into 2 blocks, one block of 64 MB and one block of 36 MB. That is how this splitting up of blocks is done. So it depends upon the block size. Now, when we talk of 64 MB or 128 MB block size, this is for our actual clusters which are there, the practical implementation of a cluster done by the Yahoo and the Googles. So when we are trying to see this thing on our own, as we have installed a single node cluster on our laptops, okay, so we can set the block size accordingly. So we'll be dealing with the small files. So we can set the block size as 1 MB or 2 MB or 4 MB and like this. Okay. So in my laptop, I've set up this block size as 1 MB. That's good enough to understand the concepts. So if 1 MB block size is there and if there is a file of 100 MB, then obviously 100 blocks would be there. A file would be split up into 100 blocks of 1 MB each. This we'll see when we work on the our cluster in this video itself. Okay, and the idea behind this big block size is to minimize the cost of seek so that we can read a file very quickly and at a streaming rate, right? Then talking of block replication, the name node is going to determine the replica placements. Like when a file is split up into blocks and its replicas are to be placed in the cluster, this is decided by name node. Okay. And these replica placements are rack aware. As I just discussed with you, that if there are different racks, then 2 replicas in one rack and 1 replica in some other rack. And this idea is to attempts to reduce bandwidth, because you see the intra bandwidth in a rack is more than the inter bandwidth between racks. Okay, so if you see the policy here about replication, the default replication is 3, The first replica is on the local rack. The second replica is also on the local rack, but a different machine. And the third replica is on a different rack. Okay. And in our case, see, this is when you have multiple machines in a cluster. Only then you can make the replicas. In our case, we have got a single node cluster. So there is one name node, one secondary name node, and one data node in our cluster. So when we put this the replication default replication, we will set it to one. Okay, we won't be having multiple replicas in a single node cluster. Then the name node, it does not directly write or read data. Okay, it is simply storing metadata. The client, it interacts with name node to update name node's HDFS namespace and retrieve block locations for writing and reading. So whenever some file needs to be stored into the cluster, name node is consulted and name node gives you the block locations that the block where the blocks should be written in the cluster, right? And the actual writing of the data, the storage of data is done by the data node, right? So I'll just review whatever I've discussed with you so far by using a different PDF with you. Just a quick recap of what we have just discussed. So when we discuss about HDFS, we say that HDFS is storage component of Hadoop. Okay, and it is a distributed file system, right? And features are obviously it's a scale out architecture. That means if we can add more machines to the cluster so that the speed of reading and analyzing can increase. High availability is there in case there is some problem. Then we always have our block at some different machine because of the replicas that we have made. Okay, it is fault tolerant and easily it can store large data sets. Okay, doesn't require special hardware. It works on commodity hardware. And it is based on the Google file system GFS and sits on top of a native file system like ext4 or ext3. And it works better with large files, right? And it is designed if there is some hardware failure, some machines go out of order, you can always retrieve your data from some other machine, right? And it is designed for large data sets, right? If you see its architecture, another example is there. Name node is there. So name node is this is a process running on an admin machine, and data node is the process running on commodity machines. There could be hundreds and thousands of such machines in the cluster. Okay, and this data node is actually storing the data, right? And name node is simply storing metadata. That is, what are the locations on which machines the blocks of the files should be there, right? And it's a master slave architecture where the name node is the master and data node is the slave, and it is a block structured file system. Okay. Now, if we talk of the name node process, it is the master of the cluster. Okay. And it only stores metadata. No actual data is stored on the name node, and it runs in RAM. It's a Java process. It's a critical machine of cluster. Simply because if the name node is not running, then you won't be knowing where all your data is stored. Okay, so you cannot retrieve data or you cannot analyze data because if name node is not working. And so we also, for that reason, we also call this name node as single point of failure. And now we have something known as high availability, in which there is a pair of active and standby name node. So we'll discuss this in due course of time. And for a single, name node, it should be running all the time, and cluster would be non-accessible if name node is down. And how name node manages all this, how it keeps the metadata, and for that there are two extra files in the cluster known as edit logs and fs image. I'll discuss about this edit logs and fs image in one of my future videos, right? So then we have got, after name node, we have got the secondary name. As the name would suggest, it would seem that this is a backup to your name node, but it is not the case. It is not a backup of name node. It is a separate daemon. And it does housekeeping for name node, and it does something like merging the edit logs with fs image, which we'll discuss, which we will see later on. Then data node is a Java process. It is storing the actual data in blocks. It is not so critical like name node because there are hundreds of data nodes in a cluster. If some of them go out of order, we don't have any problem with that. And there is a process known as heartbeat and block report. So this data node is sending the heartbeats and block reports to name node periodically just to indicate that it is working and it is alive. More about these heartbeats and block report in my future videos. And discussing now the HDFS concepts, we have block, which is the smallest unit for data storage or for reading of data. The files are broken into blocks. Blocks are stored independent of file, and default block size is 64 MB or 128. Now, how files are stored in our cluster? Obviously, the each file is split up into blocks, and block is usually 64 or 128 MB. Data is distributed across data nodes, and blocks are replicated across the data nodes. Name node maintains the register, like which metadata, which location of blocks, which data node, which block for which file is stored where. All this information is stored by the name node. Now, see, typically, what is the block size of a typical file system like ext4 or NTFS? ext4 is for Ubuntu and NTFS is for your Windows. So usually the block size for these are very small, just a few kilobytes. If we talk of NTFS or ext4, these file systems have their block sizes as 4 KB or 8 KB. Okay. And when we talk of Hadoop, HDFS block size, it is much bigger as compared to typical file system. Why this is so? Because we want to read huge files at a streaming pace. So we do it to reduce the cost of seek. Okay. So this is about the architecture of HDFS. Let's now have a look, like whatever concepts we have discussed, that how actually the file is stored in a cluster. So I'll take you to this single node cluster, which is up and running here. Okay. And here, like I can first see the file. See, if I list here, this is my Ubuntu file system, my local file system. Okay. And let me just check whether I've started. Yeah. So I've already started the 3 daemons. Okay. So obviously, if you want to start the daemons, the processes, this is the syntax start-dfs.sh. So you are starting the distributed file system services by using this command, which I've already done. Okay, already I have started these 3 processes which we just discussed in our discussion, and the name node, the secondary name node, and the data node. So what I'll do now is I will store some file here. So I'll just look for a file, say a big file. I'll see. I list this file. So this is a 674 MB file. Okay. And I told you that the block size for the cluster that I am using on my laptop is 1 MB. So how many blocks this file would be split up into? Yes, into 674 blocks. Okay. So I'll take this example maybe a little later. Let me look for a shorter file for you guys. Okay. Let's see. We have this file. There's a data set. Okay, this is 2.9 MB. You can see here. This is a 2.9 MB file. So if this file is stored into the HDFS, then it would be split up into 3 blocks. One block of 1 MB, another block of 1 MB, and the third block of 0.9. This is how it is done. And it is done automatically whenever you are storing the file in the cluster. This is done automatically. So what I'll do here is I'll store this file using some command which we'll discuss in future, a put command. Okay. And I'll store this file. This is the command to store this file into the root of the distributed file system. So first I will show you the distributed file system, the web UI of distributed file system. So you can see this is the root of the distributed file system. Okay. So as you can see, there are only 3 files here, 2 files and 1 directory. This user directory you're already aware of. User directory, below that it would be a HD user directory, and below that there would be the trash directory. Okay, you are aware of this. This we already discussed in one of our previous videos where we discussed about trash and its settings. So there are 3 files, and what I'm going to do from my local file system, here I am in my local file system. This is my distributed file system. I've started the web UI of the distributed file system. So you can see there is a data node status is there. The overview of the cluster is there. This I'll discuss with you. This I've already discussed with you in the installation of Hadoop. So you should look in that video. So you can see like how the system, this distributed file system, HDFS starts, the startup progress, what all is there and there. And then you can see browse the file system. Okay, so this is my distributed file system. Only two files and one directory are there currently in the distributed file system, that is HDFS. And with this command, if you see the command on screen, with this command, what I'm going to do is I'm going to transfer this file dataset-movies.csv into the root of the distributed file system. And this file is of size 2.9 MB. My block size is 1 MB. Okay, I've already configured it, and in the installation of Hadoop, we have already seen it. I can show it to you again here. So we have our configuration files in our default installation folder, and below that there is this folder, and below that I have the file HDFS site.xml. Okay, so if I open this file, the configuration file, you can see that there is a property named as dfs.block.size, and I've set it to 1048576 bytes. That is 1 MB. Okay, so 1 MB is the block size of my cluster. I can increase it here. I can make it 2 MB. I can make it 4 MB and so on. But remember, for our discussion right now, the block size of the cluster is 1 MB. Okay. So again, now I will write the command to transfer the file. The put command is used. This we'll discuss later on. Okay. And I'm transferring it to the root of the distributed file system. I'll show you the root here. Only 3 files are there, 2 files and 1 directory. And when I store it there, you will see when I refresh it, the file will appear. Okay, so it is still copying because it is dividing it into blocks. So after some time, it will show. So I'll again refresh it, and you'll see that the file has been copied. So you can see this file dataset-movies.csv has been copied, and obviously no message comes here. Actually, here it's simply if the no message is there, then the file has been transferred into the distributed file system. So you can see here that the replication is 1, the block size is 1 MB. This is the size of the file 2.81 MB. This is the owner, this is the group, okay, and these are the file permissions. So these file permissions, what they mean, we'll understand it in our future videos. So I'll just open up this file to show you actually what we discussed in the architecture of HDFS. Remember, this file is a 2.81 MB file, so it should be divided into 3 blocks, and you can actually see the blocks here. You can see the block information. Block 0 is 1 MB. I hope you can see it on screen, right? If you look at this block 1, this is the second block, again 1 MB, and the third block is 845421 bytes. So as I told you, this is like split up into blocks depending upon the block size of the cluster. Since the block size is 1 MB, so a 2.81 MB file would be split up into 3 blocks, 2 blocks of 1 MB each, that is block 0 and block 1, and the third block of the remaining size, right? So let's now store a bigger file, and before I do that, I will tell you actually where these blocks are stored in our distributed file system. For that, I'll click on files here, and I will click on computer. Then I'll go to my cluster location, that is user. Then we have local, and then Hadoop store. If you look at my installation video, you'll understand where I'm taking you. I'm taking you to the data node, and data node has been stored under this folder. And there is a HDFS folder, and this is the data node and the name node folders. This we configured when we installed Hadoop. So kindly look at that video carefully to understand what I'm doing here. And below data node is a current folder. Then there is a block pool folder. Then there is a current folder. So these are the, here actually in the finalized folder, there is a subdirectory 0 folder, and there would be further subdirectories, okay, where your blocks would be stored. Okay, So if we look at say subdirectory 17, so we need to actually look at it where it is stored. Okay, so maybe in subdirectory 18. Yeah, these are the three blocks that we just stored. And remember, with each block there is a checksum.meta file. Okay, so checksum you would have already studied in your previous semesters. Checksum would just ensure that the correct file, an uncorrupted file has been stored in the cluster, right? So these three blocks are there, and each block has got a checksum file. Okay. So what happens here is, kindly understand very clearly that while you are transferring the blocks into the cluster, so here you here are the the RBW folder is there, okay, and this is the finalized folder. So first of all, the block that is to be written, it comes into this RBW folder, okay, and it is replica before writing. It is first verified, okay. RBW is a replica before writing. Once it is verified, then it is shifted to finalized. Okay, so right now you can see this RBW folder is blank. Okay, so I'll just keep you in this RBW folder so that you can actually see that when huge files are stored, the replicas first come here, the blocks, okay, and after that they are shifted to finalize. So we'll keep our focus, we'll keep this block opened here. We are in this RBW folder, okay, and now I will transfer a bigger file, okay. Now I will transfer a bigger file for you. Say, you can see this file. I'm transferring this file, Hadoop 3.3 this. Okay, so if you see the listing here, this file is 674 MB. So it will be split up into 674 MB blocks. Okay, with names as block 0, block 1, block 2, so until block 673. Okay, and as these blocks are being written, you will see them here in this RBW folder. They'll appear here and they will disappear. Okay, I hope it's clear. Now let's start the process. This has started. Now look at this folder. Once the process starts, the replicas would be coming here. The blocks would be coming here. Each block is being verified along with its meta file, and it is going to which folder? It is going to this finalized folder. Okay, so 670 blocks verified and getting stored. Okay, and when you look here in your this thing file system, and if you just refresh it, you will see that this file is being copied, is in the copying process. Okay, you can see it here, it is being copied. Okay, so far 527 MB has been copied, so very transparent to the user. If I again refresh it, it will show you it is now 673.8, that is the actual size. Okay, so 673.8 would mean 673 blocks of 1 MB each and 0.8 MB of another block. So if you look at it here, okay, you will see all those blocks here. So I hope you understand. You will have all the blocks here till block 673. All the blocks here are 1 MB in size, whereas this block 673 MB is 0.8 MB in size. So as I told you, the HDFS architecture is very transparent to the user. The actual storage you can see here now. This RBW folder is empty because the replica before writing has been verified, and it has now gone here. And you can see there are further subdirectories, okay, and which would contain a lot of files here. Okay, so if you see, there would be a lot of blocks now, lot of blocks, 670. So along with that, there is some dot meta file also. So you can see that this process is very transparent in your cluster. Okay, and with that, I come to end of today's lecture, and just a quick recap. I've discussed with you about the HDFS architecture and about how the files are stored in a cluster, and I've also shown you the actual storage of the blocks after verification into the cluster. And you can see that this process, whatever we studied in the theory part, is very transparent to the user. In my next video, I'll be discussing with you about the HDFS commands. So I'll be taking up a series of 4 or 5 videos in which I will discuss and execute each HDFS command with you. Till then, keep watching the videos. Thank you very much.